Let's go to FET biasing. When we say FET biasing, we have three FETs: JFET, E MOSFET, D MOSFET. What are the basic equations? When you say JFET, ID is equal to IDSS into 1 minus VGS by VP whole square. And when you say enhancement MOSFET, ID is equal to K into VGS minus VT whole square. When you say depletion MOSFET, ID is equal to IDSS into 1 minus VGS by VP whole square. These are the three basic equations we need. And if we see corresponding characteristics, this is ID, IDSS, VP. For the second one, VGS ID, VT. For the third one, VGS, VP. These are the three different characteristics: JFET, VI equation, characteristics; enhancement MOSFET, VI equation, characteristics; depletion MOSFET, VI equation, characteristics. Suppose you get two negative values here. Here you should take negative value. If you get two negative values, the condition is VGS is less than VP. Okay. So you are very clearly seeing that VP is negative. But if you are getting both negative values because of the quadratic equation, you should take VGS less than VP. Similarly, in enhancement MOSFET, VT should be positive, VGS should be positive. If both are positive, you must take VGS greater than VT. So here VGS is negative, here VGS is positive. If both are negative, take whichever is lesser. If both are positive, take whichever is greater. Similarly, here this can be any value. So, but modulus should be less than VP. Because you can have if you take more than this, you are at this. So, this is generally for depletion mass in depletion mode. But one thing is very clear, and if VGS is positive or greater than VP, this is called depletion mass enhancement mode. So these are the three simple ideas: VI equation, characteristics, condition. VI equation, characteristics, condition. With this you can talk about how to calculate the values. That is called biasing of FET. With these equations we will go and see how to bias them, what is required. The second point is DC load line. DC load line. For example, look at these characteristics: VDS versus ID, VGS -1, VGS 0. I am talking about JFET, output characteristics. Okay. Suppose this is 0, 2, 4, 6, 8, 10, 12. 1, 2, 3. ID is milliamperes. VDS is volts. Then the question is, for VDS equal to 2 volts, what is ID? For ID is 1 milliampere, what is VDS? If you see that question, for example, if you draw a line at 2, you have two values. So you cannot know this. If you draw at 1 milli, you have two values. One value here, one value here. That's why this output characteristics cannot give output values. There is no direct relation between output voltage, output current. That's why when there is no direct relation, how to achieve that? For that we have to go for DC load line. For example, take a JFET, VDD, RD, RS. Say there is a capacitor here. VDS, ID. Because generally gate current is 0. Same current comes here. And this capacitor, open circuit for DC, short circuit for AC. For DC, capacitor is open. For AC, capacitor is short. Let me also tell you why it is so. For example, impedance of a capacitor is 1 by J, 2 pi FC. And for DC, what happens is frequency is 0, therefore impedance is infinity. Infinity means open circuit. That's why I have written open circuit for DC. Similarly, 1 by J, 2 pi FC, for AC it is not 0, therefore ZC tends to 0. When the frequency is not 0 and C is large, because just a frequency is not 0 and C is any value, it's not possible. F has to be there and C must be larger to make this as smaller. That's why when I write any short circuit, I mean that large capacitance. That's why please understand the capacitance here is very large. Capacitance is very large. When the capacitance is large, that's why we say this is 100 micro. And you know, this capacitor is called bypass capacitor. It's bypass because it is bypassing the RS. And bypass capacitor is the largest of all capacitors in amplifier. That's why in order to make this as 0, this has to be larger for any value of F. These are the two things to explain how this is existing. So short circuit for AC and open circuit for DC is this explanation. With that I will continue and see what happens. When you talk about DC, this capacitor is open, therefore RS present. So let me apply KVL for DC. VDD minus IDRD minus VDS IDRS 0. From there, ID is equal to 1 by RD RS into VDD plus VDS into 1 by RD plus RS. It's like Y is equal to MX plus C. that is slope is 1 by Rd plus Rs, because y is mx plus c. And now you ask for the same equations. For VDS 0, what is ID? For VDS 0, ID is VDD by RD plus RS. For ID is 0, VDS is VDD. Now with these two values, I can draw a statement here, somewhere here. This is VDD by RD plus RS. Now what is happening? If you ask the same question here, for VDS2, what is the current? There is no two values, you have only one value. And for ID is equal to 1, you have only one value. Therefore, without DC load line, you cannot have a direct relation, but with DC load line, you have a direct relation. Therefore, DC load line gives direct relation between output voltage and output current. That's the very definition that I have given. What is the main purpose of DC load line? I said it gives a direct relation between output voltage and output current. By the way, why do we need a direct relation between output voltage and output current? For example, take a tube light. It requires a voltage rating and current rating. Okay. Take anything, any load in this world electrically. It requires some voltage and some current. With one specification, no load works. So when you are saying this loudspeaker is working at this voltage, it also requires some current. Every element has two specifications. There are two specifications required for every element. So if one is maintained and the other is not maintained, that's not possible. Therefore, you have to go for every element with two specs. That's why it has a voltage rating and current rating where it's working. So this is called DC load line. So first we have seen VI equations and the basics of device. Now we are going for DC load line. That's meaning of DC load line. Third point is quiescent point. Quiescent point. The word quiescent means sleeping. Indirectly, absence of signal. When it says signal is absent, I am simply saying it is a DC point. It is specific value of DC load line. What's happening is, in a DC load line, you have a relation between output voltage and output current. For example, if you look at here, as we just now discussed, ID, VGS minus 1, VGS 0. Suppose this is DC load line. And suppose if you are taking Q point here, this is called one of the values of DC load line. And the signal will be going through that. That's why this Q point is also called operating point.